Well, when we finish, you can absolutely teach me that. As long as I don't show up on any social media. Andrew, yes, sir. Uh, let's hold on. Okay, just because we're starting the lesson, we're just really close. Okay. All right, so we're not going to go ahead and do a whole lot today. We spent the majority of the time talking about the test. Remember, you have until Thursday morning, 8:05, if you want to retake that. Come on in. But we've been talking about vectors. And one aspect of vectors we've been talking about quite a bit is that component form. Okay, and it looks and acts just like an ordered pair, but we know it's a vector because of those arrows on either end. Remember, A represents the horizontal distance. It moves you left or right, while B is the vertical distance. That's going to move you up and down. And then we have some notation. We got some vocabulary. Magnitude is typically going to refer to the length, the speed, etc. of a vector. And here's the notation. It's the double bars that you put on variable, like if I want to say the magnitude of vector v. So that formula right there is the square root of a squared plus b squared, and you take those values right out of the component form. Okay, and a vector itself, it starts at what we call the initial end, it ends at the terminal, that's the end with the arrow. What do we call it when the initial is at the origin? That's standard position, and we love to put vectors in standard position. Okay, and we've been working the other day. We were looking at the triangle method, and we talked about how it's very important when you're creating the triangle to always put a terminal and an initial point together. We don't put two terminals, we don't put two initials together. Now, when you put the third side, that's perfectly fine, but not initially with the two. Okay, and then I think we started getting through these right here, right? Okay, so let me give you a couple of review problems real fast. Let's say I have, this is going to be something completely different. Let's say I have vector u is 3, -7, and I've got vector v is equal to -4, 5. Okay. Let's say I want to perform some operations with these. What if I simply wanted u plus v? What do I do? There you go. That's exactly right. Just add or subtract the corresponding values. I know that 3 corresponds to -4, so that it would be -1. And then -7 corresponds to 5, so that would be -2, just like that. Oh, the composition? In a matter of speaking, yeah. Okay. What if I had a scale factor? What if I wanted to show -3 times u? There you go. It's just like a distributive property for vectors. So what's -3 times 3? So that would be -9. And then -3 times -7? +21. And there you go. That's operations. Oh, well, my pen kind of hit it. That's a 21. There you go. That looks like a what? Oh, took off the wrong one. There we go. It's why. There we go. Okay, so that's what we were talking about the other day. Right, Andrea?
Yeah.
There you go. Okay. Right, Daniel? Okay, there we go. All right. Okay. And let's see what we got here. Okay. Well, let me go ahead and introduce an idea to you called unit vectors. Okay. It says if v is a non-zero vector in the plane, then the unit vector is a vector in the same direction as the original vector with a magnitude of 1 and is given by this formula. Okay. So all you do, and this one, I don't know why they changed it like this. That should actually be a v right there. But you take the component form of a vector and you go ahead and divide it by the magnitude of that vector. So here is big picture what we're talking about. Let's say we have a vector u, okay? And let's say, the magnitude is 5. And we're talking about the length of the vector. So it's 5 feet long. Let's go ahead and say that. Well, a unit vector is going to be a vector that goes in the exact same direction, but it's only one magnitude length long. So in this case, it would just be 1 foot. It's always going to go in the exact same direction, and the magnitude would just be 1. Now, the unit vector is going to be more important to us when we start looking in the next section for what we call a vector projection, but that's the idea, and it's a very, very simple formula. Okay, so let me show you how we do it. Here is my problem. V equals negative 515. There's my component form. Okay, so what I want to do is go ahead and find a unit vector. A vector that's going in the exact same direction, but is only 1 unit long. Okay, so a very short vector. All right, so here's what I'm going to do. According to the formula, I'm going to take V, the component form, and I'm going to divide it by the magnitude. Now, we already have the component form, so I'm just going to go ahead and say negative 515. But how do I find the magnitude of a vector? What was that formula we had? All below what? So he says the magnitude of V is going to be a squared plus b squared, but it has to be below square root. Yes. That's how we find the magnitude. And remember the component form, that is a and that is b. So let's see here. This will be the square root of, well, negative 5 squared plus 15 squared. Okay. So let's see here. What is negative 5 squared? 25. 15 squared? 225. So I'm looking for the square root of 225 plus 25. 200, 250. That's right. Now, this is one of those times where we want to leave it as a radical, but simplify it if possible. This one will break down. Can anybody tell me what's the largest perfect square that will divide 250? It is 25. In fact, 25 times what? 25 times 10. So see, I can take the square root of 25, but if I take the square root of 10, I'm going to get a decimal. We don't want that. So this is going to be 5 square root of 10, right? So that's my magnitude. So all I'm going to do is come back over here in the formula for my denominator. I'm going to put 5 square root of 10. Okay. So now all I have to do is simplify this, and I've got what's called a unit vector. Okay. So how do we simplify that? Well, I'm glad you asked. You'll just take each of these values, the a and the b, and you'll divide each one by that magnitude. So the first one, I would have negative 5 over 5 square root of 10. And then I would have 15 over 5 square root of 10. And then you just go ahead and simplify. Okay. Well, let's see. What can, oh, yes, sir. What can simplify in the first one? There you go. Because the 5s are going to cancel. So I'd be left with a negative 1, right? But see, we have negative 1 over the square root of 10. We want to rationalize. So let's say if I put this over here, negative 1 over the square root of 10, we'd have to multiply by the square root of 10. So what would I get for the first value? Negative square root of 10 over 10. Is everybody okay with that? Now, in the other part, the 15 fifths, that reduces to 3 over the square root of 10. So what would that be if I rationalized it? That's exactly right. 3 square roots of 10 over 10. That's your unit vector. Now, let me go ahead and show you exactly what this means. Okay? Think of this as an ordered pair. The original vector, V right here, think of him as an ordered pair. What quadrant would he be in? Oh, not the first one. Why 2? Because, see, the A value is negative, so that would tell me to go left, and then the B is positive, so that tells me to go up. So whatever vector V looks like, it goes over like this, right? There's V. So what we just found right here is the component form of a vector that goes the exact same direction, but it's how long? Just 1 unit. So it's like a baby vector. No. What? Why can't we talk about babies? We're not talking about the process of making a baby. Now that's something we can't talk about. Yeah, that's another class. I mean, some of my best friends used to be babies. So. Because they grew up. They used to be. We all used to be babies. Yeah. Okay. All right. Well, we're gonna go ahead and stop there. There we go. All right.